Hey guys, Mr. Mustafa here. In this video we're going to learn about differentiation of trigonometric functions. If you have not watched my previous videos on differentiation rules, make sure to check the link out in the description box just below this video. Right, so let us get straight into trigonometric differentiation. So what is trigonometric differentiation here, guys? So as you have seen with my previous videos, I usually start off with a general rule, right? So let me just give you the general rule for this. Right, so the general rule is if we have a function y is equal to cos x, if we have a function y is equal to sin x, right, then y prime will become cos x, and if you have a function y is equal to cos x, the derivative of cos x will become minus sin x, right? So these things are results from first principles. You know, first principle example, if you let y equal to, let f of x be equal to sin x, right, then your first principles, these results comes from first principles and using limits, right? So you need to know those stuff. So f of x is equal to sin x, then f of x plus h is equal to, let me just write it here. What's first principles? F prime x is equal to limit as h approaches 0 of 1 over h, or what people say is f of x plus h, basically f of x plus h minus f of x all over h. If you do this type of stuff, then you'll end up with, obviously you need to know how to do compound angles and stuff. So limit as h approaches 0, f of x plus h is, we kind of proving like the derivative of sin x is cos x, right? So f of x plus h, which is sine of x plus h minus sin x all over h. Now instead of writing 1 over h, instead of writing all over h, let me just write 1 over h. Limit as h approaches 0 of 1 over h into sin x, sin h, expansion for sine, compound angle for sin x plus h is sin cos, plus cos x sin h, right? Subtract the sin x. Now I'm going to try and simplify this as far as possible. So we can see over here we're getting sin x as a, we've got sin x here and we've got a sin x over here. So we're going to take out a sin x as a common factor and take the limit inside as well. Limit as h approaches 0 of sin x into cos h minus 1 all over h. That's what we have, times limit as h approaches 0 of cos x times sin h. Limit as h approaches 0 of cos x times sin h. Well, I took this h over there. I took this h over, should have two h's, yes, sin h over h, because we have two terms. I'm combining this term and this term, right? So, and I'm adding times 1 over h times this, yes, with the limit as h approaches 0 of 1 over h times this, limit as h approaches 0 of 1 over h times these two. Right, so anyways, what this here becomes. So sine x is just remember the function is in terms of h. As h approaches 0, so sine x is a constant, so sine x into limit as h approaches 0 of cos h, it's not cos, it's cos h minus 1 over h, right? If you pronounce it as cos, then that becomes a hyperbolic function. It's not a hyperbolic function, it's just cos h minus 1 all over h times, sorry, not times, supposed to be a plus here. Why did I put a times? It's supposed to be a plus. That was a plus there. Plus cos x into limit as h approaches 0 of sine h over h. Now this part over here is equal to 1, right? There is a proof in mathematical text where limit as h approaches 0 of sine h over h is equal to 1, or you can just use a short form of L'Hopital's rule. You can see you're getting 0 over 0, which is an indeterminate form of L'Hopital's rule. You can differentiate the top, you're getting cos h over 1, directly substitute, and you should get 1. Same story here. If I substitute 0, you're getting 1 minus 1 over 0, so 0 over 0, indeterminate form of L'Hopital's rule. Differentiate the top. Well, we don't know what's the derivative of this, we kind of finding, so let's see. So you can't actually use the L'Hopital's rule here because we kind of investigating that the derivative of sine x is cos x. So you need to find the limit over here, because that sine h over h is actually 1. So we are getting cos x over here, right? And this is basically sine x times 0. So this is basically equal to cos x. Now I'm going to show you why this limit is actually 0. So note, limit as h approaches 0 of cos h minus 1 all over h. So how can we simplify this? Let's see if we can apply some cos h minus 1 all over h. Why is this limit equal to 0? So let me multiply by this by the conjugate, make it cos h plus 1 over h, cos h plus 1, and use this rule here, sine h over h. So limit as h approaches 0 of sine squared h minus 1 all over h into cos of h plus 1 is equal to, now sine squared h minus 1 is actually supposed to be cos squared. Why did I put sine squared? Should be cos squared h. Cos squared h minus 1 is actually negative sine squared, so negative limit as h approaches 0 of sine squared h, negative sine squared h, so 1 minus cos squared h is sine squared h all over h into cos h plus 1. Right, so now we're going to break this up into, because we know that limit as h approaches 0 of sine h over h is equal to 1. We know this result. Right, since we know this result, we can apply this result here. So let me break this up and simplify. So that's negative limit as h approaches 0 of sine h over h, right, times limit as h approaches 0 of sine h, should be sine h all over cos h plus 1. Yes, So if I directly substitute, so remember this is 1, so negative into 1, right? Applying this rule here directly. That's negative 1 times. If I directly substitute here, I'm getting 2 in the denominator, 0 on top, so that's 0 divided by 2, and that final answer is just 0. So we have the answer here. So then we have just proved that the derivative of sine x is cos x and the derivative of cos x is sine x. So how about the rest? Right, so the rest of the derivatives, which is, so we have y is equal to sine x, right? And we have y prime here, which is cos x. Then if we have, what about the rest? Cos x, then we got sine x, cos x, you get negative sine x. You can apply first principles there. For the rest, we don't apply first principles, we use the result of the first two. Then tan, the derivative of tan will give us sec squared x. The derivative of cosec x will give us negative cosec x cot x. The derivative of sec x will give us sec x tan x, and last one, the derivative of cot x will give us negative cosec squared x. So for the derivatives of the last four, right, we can just apply the table over here, right? For the derivatives of the last four, we can just apply this table over here and write sec tan cosec negative cosec cot. So how this table works is that if I differentiate, see, if I differentiate sec x, I get sec x tan x. If I differentiate tan x, I get sec times sec, which is sec squared x. If I differentiate cosec, I get negative cosec x cot x. If I differentiate cot x, I get negative cosec squared x. So if you differentiate one of them, you get the other two. So that's the beauty of this table. Now let us look at an example, or sorry, let's prove one of them. Let's prove that the derivative of tan is sec squared x. So we'll prove that d dx of tan x is actually equal to sec squared x. So how? So we can say let y equal to tan x. We know that tan x is actually sine of x. We know that tan x is actually sine x over cos x. So sine over cos is in the form f over g, so we can't forget about quotient rule. If you have not watched the video on quotient rule, make sure to check the link in the description box just below this video, and that will take you to quotient rule and you can learn the quotient rule from there. So quotient rule says f prime g minus g prime f over g squared. So I want to find the derivative. The derivative of sine x is cos x, leave the denominator, times cos x, minus the derivative of cos x is negative sine x, and leave the numerator, which is sine x, all over the denominator squared, and the denominator squared is cos squared x. Now cos squared, what we have now is cos squared x plus sine squared x, right, all over cos squared x. And what do we have? We have 1 over cos squared x, which is equal to sec squared x, and that is now the derivative of tan, which is sec squared x. Let's look at another one. So let's see, 1 2, that was number 1 and that was number 2. Let's call this number 3 here. Let's look at the next one, which is cosec. How come the derivative of cosec is negative cosec cot? Same. Again, apply quotient rule everywhere. For this entire table, you just need to apply quotient rule. Okay, I will do cosec x and then you can figure out what is sec x and cot x. You should follow the same idea behind this. Number 4. So if I have ddx of, how come the ddx of cosec x is equal to negative cosec x cot x? So what we need to say is let y equal to cosec x, and we know cosec x is 1 over sine x. And to find the derivative of 1 over sine x, derivative of 1 is 0, so 0 times sine x, subtract, derivative of sine x is cos x, leave the top, which is 1, divided by denominator squared. Denominator squared is just sine squared x. So what I will do now is I will break this up into 2 parts. So I'll break this up into negative cos x over sine x times 1 over sine x. Right, or let's write it like this. Let's put 1 over sine x first, right, and then say cos x over sine x for the second part. Cos x over sine x, and we can clearly see that negative 1 over sine x is negative cosec x, and cos over sine is cot times cot x, and that's a derivative of cosec x. And similarly you can do number 5 and number 6, how to find the derivative of sec x and the derivative of cot x. Right. Let's differentiate. Now how do we differentiate? So let's take an example. Right, now we are doing the actual example because those were just proofs. So example 1, so we will get stuff to differentiate like this. So we get y is equal to sine of 2x squared minus 3. How do we differentiate it? So we start from the outer and we go on the inside. So we are applying kind of chain rule. So you're going to say, alright, so y prime is, derivative of sine of the whole thing. Sine of, think of this as an angle. What's the derivative of sine of the angle? Is cos of the angle. So cos of 2x squared minus 3, right? That's sorted out. And then differentiate the 2x squared minus 3. You will get 4x. So that's your final answer. Let's take example 2. Let's say y is equal to sec, let's make it a bit complicated, sec e to the power 5x, right? So y prime, if I want to differentiate sec, I get sec x. Now you can't say sec x now because that's your argument, e to the power 5x. So you're going to say derivative of sec is sec tan, so sec e to the power 5x, tan e to the power 5x, and now you need to differentiate e to the power 5x, which is this e to the power 5x times 5, and that's your final answer, unsimplified. Example number 3, if I want to find the derivative of, look at this nice problem here, which is cosec cubed 5x squared minus ln x, 5x squared minus ln x. Yeah, let's make it a bit difficult. Right, how are we going to do this? Well, we got a problem because we can't differentiate cosec cubed, so we need to rewrite this in the form that we need. So this is in the form cosec 5x squared minus ln x to the power 3, like that. So now we find y prime, need some space, so chain rule first. 3 cosec 5x squared minus ln x squared times the derivative of the inside. Now you're just differentiating the inside now because you finished to the full. If I differentiate the inside, derivative of cosec is cosec cot, negative cosec cot. How we know that? Look at this table. Derivative of cosec is negative cosec cot. So that's negative cosec 5x squared minus ln x times cot 5x squared minus ln x times the derivative of the inside, right? So the derivative of the inside, which is 10x minus 1 over x, and that's your final answer. Right, so let's simplify everything. We can simplify as far as possible. This is minus 3. Let me bring the other bracket at the end to the front. So 10x minus 1 over x, 10x minus 1 over x. Then we can see that this part over here can be combined. This part and that part can be combined. It can just become cosec cubed 5x squared minus ln x, and that is just cosec cot, not cos, times cot 5x squared minus ln x, and that should be your final answer. I try to simplify as far as possible. How about this example 4? I want to find the derivative of this function. Y is equal to sec x times tan 3x. Right, so you can't take this as sec tan. Right, so we're finding the derivative of this. To find the derivative of this, we're going to apply the product rule. So we're going to say y prime is now equal to derivative of sec x is sec x tan x. I'll leave the tan 3x as it is, tan 3x plus, if you don't know how to do product rule, make sure to check the link in the description box to take you back to product rule over here. So sec x tan x times tan 3x. Right, so I finished differentiate sec. Let's take this as f and g. This is f and that is g. So I just found f prime for now and I left the g. Now I'm finding g prime. The derivative of tan 3x is sec squared 3x times 3. Where did I get the times 3 from? You need to differentiate that. Now let's see if the derivative of tan 3x is sec squared using the table. Derivative of tan is sec squared angle, which is 3x times 3, and then leave the first part as it is, which is sec x. So there's your second part, which is g prime, and that is your g function. So what's the final answer? Final answer is obviously can't combine these. Okay, I'll just leave it like this, unsimplified. You go and try and simplify. How about this? Let's look at one with the ln, example 5. If I want to find the derivative of ln sin x, what's the derivative of ln sin x? If I have y is equal to ln sin x, then y prime will become sin x. Derivative of sin x is cos x over sin x. Amazing. So you can simplify this. This is just cot x. So the derivative of ln sin x is actually cot x. I hope you understand, guys. Thank you. Don't forget to watch the previous videos on logarithmic differentiation. If you don't know any one of the forms of the differentiation as presented here, you can always go back and watch the rest of the rules. I hope you understand, guys. Thank you.